In today's video, we're going to be solving company queries 1. This problem involves a dynamic programming technique called binary lifting. Let's read and then we're going to implement it in C++. Also, go easy on me because I started learning C++ like 4 days ago, maybe. A company is n employees who form a tree hierarchy where each employee has a boss except for the general director. Your task is to process Q queries of the form: who is employee X's boss, K levels higher up in the hierarchy. Input: the first line has two integers n and q, the number of employees and queries. The employees are numbered 1 to 2 to n, and employee number 1 is the general director. The next line is n minus 1 integers, e sub 2, e sub 3, all the way up to e sub n, for each employee 2 to 3 to n. Their boss. So what that means is basically this is what would be employee 2. So the indices go from 2 to n, and that serves as the employee. The value at said indice is the boss of the employee. So the boss of employee 2 is 1, the boss of employee 3 is 1, the boss of employee 4 is 3, 5 is 3. Now, I guess I'll draw out our tree really quickly. We are looking to find we're looking to find node n's kth ancestor, or x's kth ancestor. So we're looking for fourth's first ancestor. The first ancestor of 4 is node 3. We can see that there. Then we are looking for fourth second ancestor, so we go from 4 and then we go from 1. We go to 1, right, because that's the second ancestor, so the answer here is obviously 1. And then we're trying to find the third ancestor of 4, so we go 1, then we go 2, but this boy is our CEO. He has no boss for bro, right? Which means we will just return -1 from there. An observation you could make in dealing with cases like that first is that if k is greater than the depth of our current node, right, then it is impossible to go up that amount, right? So the depth of your node must be at least k. It must be greater than or equal to k for you to go up that amount, right? And that's just a simple observation you can make, right? Because if there was another edge like right here and we wanted to find the third ancestor, there's 1, 2, 3 edges that we can traverse, so we can go up there. And that's just really simple to get the depth. And then to calculate the parent, basically you would have U and P, and then you'd have an external like global parent array, and you just say the parent of node U is just equivalent to P, right? And then calling it, right, we'll assume 1-based indexing for now. We'll just pass in 1, 1 because the CEO's boss is, himself. So that's kind of how we'd set up the parent array and the depth array. The first approach you would probably come up with, given the parent array, is just to traverse its implicit hierarchy, right? It would be very simple to do so. So after your initial check to see whether depth is at least greater than or equal to k, you would just run k times and traverse the parent array. So you'd have like cur would equal the node that you're given, right? And you go for I equal to 1. This will just go to k, right? You'll just say cur equals parent at cur. And then here you'll just return cur. You see what I'm saying? So it's like, that seems simple to do, but let's think worst case scenario with this graph. You should probably think about that yourself first before I spoon feed it to you. So, all right, now I'm gonna spoon feed it to you. So worst case scenario is that the depth of our tree is n minus 1, right? Meaning that there's no branching, right? It's just one contiguous like path from root to leaf, right? So there's one root and there is one leaf. At most that's n minus 1, but if we want our upper bound, that's basically n squared. And I don't know if you've observed the problem, but 2 times 10 to the 5th squared is just not feasible. The second approach you might think is, okay, well, if accessing worst case is like O(n) squared for all q's, so qn squared, right, for all queries, then let's just pre-compute everything. But if we did pre-compute everything inside of an array, that would most definitely exceed our memory, right? So we also can't pre-compute it. We have O(n) access to, the node's kth ancestor, but storing it like that is just not a good thing to do. Is bad. Tell me why he ain't nothing but a heartache. Tell me why I ever wanna hear you say. Oh,